How can we place 8 queens on an 8x8 chessboard so that none of them attack each other? We will be solving this problem using backtracking. The algorithm can be applied to any n×n board for n queens if a solution exists. The code will be presented in Python. How does a queen attack? A queen can attack vertically, a queen can attack horizontally, a queen can attack diagonally. The brute force approach is to place a queen on each square and check if any queens attack each other. It is more efficient to skip squares we know are under attack. By skipping a square, I mean we do not place a queen on that square. All squares should be checked by brute force. We will use a Boolean array to track which rows, columns, and diagonals are under attack. If a column is under attack, we will mark the column as true. If a row is under attack, we will mark the row as true. If we subtract a column index from the row index, we see that the diagonals can be indexed. We see that the range is always n plus n minus 1 that we double counted. We want a zero-base index for the diagonals. We can get a zero-base index by shifting row minus column by adding n minus 1. For the anti-diagonals, we can add the row and column indexes. We do not need to shift the anti-diagonals since we already have a zero-base index for the anti-diagonals. Here is the recursive code in Python. We will be using the stack to keep track of which row we are on. Since we know only one queen can occupy a row, there is no need to also use a Boolean array to look up which row is under attack. Our initial call to solve will push row 0 onto the stack indicated in the bottom right corner. Every time we place a queen on a safe square, we mark the columns and diagonals as under attack. We will recursively call solve for the next row since another queen cannot be placed on the same row. In our recursive call, we will also append the newly placed queen's row and column position to our solution list. When we backtrack, we return to this line and remove the queen from the row, allowing us to continue searching the row for another safe square. We also mark the columns and diagonals as safe and iterate right on the same row for the next safe square. When a queen is placed, we will mark the corresponding index of our Boolean column array as under attack. When a queen is placed, we will mark the corresponding index of our diagonal 2 array as under attack using row minus column plus n minus 1 as the index. When a queen is placed, we will mark the corresponding index of our diagonal 1 array as under attack using row plus column. Now to step through the recursive backtracking, we start by calling solve with row 0, empty Boolean arrays, and empty solution list. We push row 0 on the stack. If our solution list has n tuples of row-column pairs, we have a valid solution. Remember, Python tuples use curved parentheses. We start at row 0 and column 0. Current row and column numbers are highlighted in yellow along with the square. If a square is safe, we place a queen there and mark Boolean arrays as under attack. We recursively call row plus 1 and pass in current Boolean arrays along with solution list that has newly placed queen added. Recursive calls just push on the stack. We then search for the leftmost safe square on the next row to place a queen. Our function is complete when we get to the end of a row, meaning we have fully explored the row, so we pop the function off the stack and backtrack. We then return to the state where we push the function on the stack and continue from that point. This is where we remove the queen, which means we should also unmark our Boolean arrays. We then continue to iterate right on the same row to find the next safe square to place a queen. I am going to fade out our current progress and fade in close to a solution. In this new state, we have just placed a queen on row 6 and will push row 7 onto the stack. Having just placed a queen, we mark our Boolean arrays as under attack. We push row 8 onto the stack but row 8 does not exist, so we must code a terminating condition above where index out of range error will occur. This guarantees error code will never execute as our recursive function has already terminated. Before exiting, we want to save our solution. Return will end our current recursive function and pop it off the stack. We return to the point where the function was pushed onto the stack and remove the queen. Unmark our Boolean arrays. And iterate right on the same row for the next safe square. Reaching the end of the row completes our function and pops it off the stack. We backtrack to the point where the function is called. Backtracking recursion continues exploring until all possible solutions are found.